Welcome to the overview of Design of Feature Extraction Engine for Speech Recognition System with 16 kHz Sampling Frequency. Implemented by High Performance Reconfigurable Computing System Engineering Laboratory, Indian Institute of Information Technology Design and Manufacturing, Kanchipuram, Chennai 6,127. Objective of this project: design, modeling, implementation and demonstration of speech feature extraction engine for speech recognition system with 16 kHz sampling frequency. Extraction of speech feature from the input voice from microphone. Extracted speech feature is searched against the stored database to convert into speech in the form of text. The generic block diagram of the speech recognition system is shown here. Speech recognition system will convert input speech signal into the text at the output. It has four major blocks in its implementation. 1. Analog to digital converter. 2. Speech feature extraction engine. 3. Search engine to search the feature in the database. And 4. External memory to store the database. This work focuses on the design, modeling, and implementation of speech feature extraction engine. The feature extraction engine has 6 stages and is as follows. First stage is framing and windowing, second stage fast Fourier transform, third stage spectrum magnitude computation, fourth stage is Mel bank energy computation, fifth stage is logarithm of energy spectrum computation, and followed by sixth stage Mel feature vector computation. The specifications of the feature extraction engine as follows. The architecture uses 16 kHz sampling frequency with 25 millisecond frame period and 15 millisecond overlap period to generate 12 MFCC coefficients. For every 25 millisecond, one need to capture the input frame, which has 15 millisecond overlap period. For 16 kHz sampling frequency, one may get 400 sample over 25 millisecond. Hence, each frame has 400 samples ranging from 0 to 399 is shown in the figure. To compute the FFT in the next stage, these frame is padded with 0 from 400 to 511. Each frame overlap period is 10 millisecond, which means every 160th sample of current frame, next frame will start. 512-point fast Fourier transform design is implemented by designing 16-point FFT followed by 32-point FFT. Initial computation is done for the column-wise using 16-point FFT hardware, and its output is fed to 32-point FFT hardware to do the row-wise computation. In each bank we need to store 256 coefficients. In 20 banks requires 5120 memory locations to store the Mel coefficients. We have optimized the storage by storing only non-zero coefficients. As a result, 5120 memory locations reduced to 480 locations. We optimized memory space around 90%. We have developed control logic to read and write these values properly. 20 by 256 filter bank is obtained and it requires 5120 memory locations. The size of the matrix is reduced by reordering and omitting the zero magnitude elements of the matrix into 480 elements. Methodology followed in the design for the functional module. Adder, recursive doubling based carry look-ahead adder. Multiplier, data tree structure. MAC design, fused MAC implementation. FFT computation, hierarchical design. Logarithm computation, hybrid lookup method. DCT computation, storage lookup. Generic block diagram of proposed feature extraction engine version 1 is as shown. The version 1 find the MFCC vectors from the absolute of FFT coefficient from input voice frame. Description of each block name in version 1 design as follows. Bank resolver, select the respective bank for operation. Address RAM, stores the corresponding address and ranges for each bank. Range selector, select the range of address for input field respect to the coefficient. Decider, decide whether each control element how it has to operate. Coefficient selector, choose coefficient value for Mach unit. Address selector, synchronously look up the values of log and cos for each bank. Hybrid LUT log, partial storage and computation of logarithm. Mach, computation unit for energy and MFCC calculation. Coefficient RAM, stores pre-computed Mel coefficients. Input RAM, stores FFT values of the input speech frame log or cos ROM. Buffers stores pre-computed log or cos values. Version 1 needs 1086 clock cycle for the FFT coefficient, 535 clock cycle for the Mel bank computation and 273 clock cycle for the DCT computation of Mel coefficients. Since the architecture is pipeline between stages, each stage is configured to work with 542 clock cycle. Timing diagram for version 1 is shown in figure for each stage signal. Hardware implementation of 512 point FFT is shown, where it uses 16 point FFT, 32 point FFT and twiddle factor RAM to compute the 512 point FFT. The architecture chooses decimation in time-based 16-point FFT architecture, which equalize the first stage hardware complexity by merging with floating point conversion module and last stage with absolute computation. Single butterfly along with FIFO and FIFO control is reused in 4 times to compute 16-point FFT's 4 stages from input to output. Optimized implementation of feature extraction engine version 2. In 32-point FFT it uses 5 butterfly to compute the 4 stages of the FFT. It has separate absolute computation unit after 512-point FFT. It has 2 max and 1 logarithmic computation units. Number of clock cycles are reduced compared to version 1. Description of each block in version 2 is as follows. Framing RAM stores the framed samples of the input speech. Mel coefficient RAM stores the Mel filter bank coefficients. Mach, computation unit for energy and MFCC calculation. FFT stage RAM stores the Fourier transform coefficients. Twiddle factor RAM stores the twiddle factors for FFT computation. Cos ROM buffers stores pre-computed cos values. Address generator generates respective addresses for all RAM blocks. Master counter control counter to generate proper addresses. Timing diagram for FE version 2 architecture with stage-wise signal flow. Details of the proposed version 2 architecture with each stage clock count and bit size is shown in the table. Feature extraction engine version 3 is shown. It has single processing element, which has 4 adder, 6 multipliers, 4 registers each of size 33 bits and 1 square root unit. The control logic is developed such a way that the underlying designed hardware can be used for 9 different functions of the feature extraction engine. It is reusing the 4 adder, 6 multipliers, 4 registers, 1 fixed to floating point converter and 1 square root hardware to infer these 9 functions. The state diagram is shown. The first frame-related feature vector will come at 2752 to 2763 clock cycles. Total of 12 features will be there each frame. 3 MHz is the maximum operating frequency of the design. Frame order in the memory location for each frame is shown, and it will also indicates how memory is reused for storing overlapped frames. Read, write scan paths of frames are shown, and it will also indicates how memory is reused for storing overlapped frames without increasing additional memory and clock count. Memory requirement for the design is shown. MATLAB results for comparison will be discussed in next slide. 12 feature vectors for 16 kHz sampling frequency in MATLAB. MATLAB result of 512 point FFT. 12 feature vectors for 16 kHz sampling frequency from including FFT in MATLAB. RTL simulation result of the proposed FFT architecture will be discussed here. RTL simulation result for the integer adder. RTL simulation result for the integer signed magnitude adder. RTL simulation result for the integer signed multiplier. The signed magnitude adder works with the frequency of 83 MHz by consuming 2.4 mW power. RTL simulation result for the single precision floating point adder. The proposed single precision floating point adder consumes 1.8 mW power, which can operate till 38 MHz speed. RTL simulation result for the 24-bit signed magnitude recursive adder Mantissa size. The module is submitted for fabrication with Skywater 130 nanometer technology node. RTL simulation result for the single precision floating point multiplier. The single precision floating point multiplier works with the frequency of 44 MHz by consuming 4.7 mW power. RTL simulation result for the single precision floating point MAC of version 1 and 2. RTL simulation result for the FIFO used between FFT butterfly stages of version 1 and 2. RTL simulation result for the fixed to single precision floating point converter. The fixed to single precision floating point converter works with the frequency of 242 MHz by consuming 0.6 mW power. The module is submitted for fabrication with Skywater 130 nanometer technology node. RTL simulation result for the single precision floating point logarithmic unit. The logarithm unit consists 4 modules as follows. 1. Log of exponent 2. Log of x1 table based on hybrid table lookup 3. Log of x1 by 2 table based on hybrid table lookup 4. Adder for 3 table result. RTL and MATLAB simulation result for the 16-point FFT. RTL simulation result of 512 point. Cadence and Vivado simulation result of FFT 16 kHz sampling frequency model. Synthesis result of each module in 16 kHz based FFT is shown next slide. Synthesis result for the 16 kHz FFT architecture. The proposed 16 kHz based FFT can operate in 3 MHz speed by consuming 18.5 mW power. GDS II of each module is shown in next slides. Tools used for GDS II. HDL used, Verilog HDL, Synthesis Tool, YOSYS, Library, Skywater 130 nanometers PDK, Simulation Tool, Icarus Verilog, GTK Wave, Flow Plan, Placement, Routing and CRC, LVS Open Road, Layout Editor, Magic. Signed adder in 130 nanometer Skywater PDK. Area 10,292 micrometer square. Power 2.4 milliwatts. Delay 83 MHz. Single precision floating point adder in 130 nanometer Skywater PDK. Area 22,536 micrometer square. Power 1.8 milliwatts. Delay 38 MHz. Single precision floating point adder for logarithmic unit in 130 nanometer Skywater PDK. Area 10,292 micrometer square. Power 2.4 milliwatts. Delay 38 MHz. Single precision floating point multiplier in 130 nanometer Skywater PDK. Area 32,172 micrometer square. Power 4.7 milliwatts. Delay 44 MHz. fixed to single precision floating point converter in 130 nanometer Skywater PDK. Area 2879 micrometer square. Power 0.5 milliwatts. Delay 242 MHz. Single precision floating point square root unit in 130 nanometer Skywater PDK. Area 48,186 micrometer square. Power 0.13 milliwatts. Delay 75 MHz. Mel Coefficient generator for 8 kHz sampling frequency in 130 nanometer Skywater PDK. Area 8564 micrometer square. Power 0.7 milliwatts. Delay 270 MHz. Twiddle factor coefficient generator unit for DCT in 130 nanometer Skywater PDK. Area 4374 micrometer square. Power 0.6 milliwatts. Delay 384 MHz. Even twiddle factor coefficient generator unit for DCT in 130 nanometer Skywater PDK. Area 2941 micrometer square. Power 0.6 milliwatts. Delay 384 MHz. 16-point FFT in 130 nanometer Skywater PDK. Area 23,127 micrometer square. Power 1.9 milliwatts. Delay 24 MHz. 32-point FFT in 130 nanometer Skywater PDK. Area 32,554 micrometer square. Power 3.3 milliwatts. Delay 24 MHz. 256-point FFT in 130 nanometer Skywater PDK. Area 2,532,761 micrometer square. Power 10.3 milliwatts. Delay 20 MHz. Mel Coefficient generator unit in 130 nanometer Skywater PDK. Area 13,851 micrometer square. Power 1.2 milliwatts. Delay 285 MHz. 16 kHz sampling frequency based feature extraction engine architecture in 130 nanometer Skywater PDK. Area 4,858,824 micrometer square. Power 18.5 milliwatts. Delay 3 MHz. High-speed signed magnitude adder with CARAVEL Society in 130 nanometer Skywater PDK. Area 10,247,840 micrometer square. Delay 83 MHz. Fixed to single precision floating point converter with CARAVEL Society in 130 nanometer Skywater PDK. Area 10,247,840 micrometer square. Delay 242 MHz. Conclusion. The proposed 8 kHz sampling frequency based FFT can able to operate till 3 MHz by consuming 15.7 mW power. High-speed signed magnitude adder and fixed to floating point converter modules are submitted for fabrication with Skywater 130 nanometers PDK in MPW Shuttle 3. Adder, logarithmic unit, square root unit, and the FFT coprocessor used in the proposed FFT architecture are the indigenous designs for the FFT architecture. Along with FFT, single precision floating point MAC, 8-point FFT, 16-point FFT and 256-point modules also generated. We acknowledge Dr. Debashis Datta, MEITY, Government of India. Dr. Sunita Verma, MEITY, Government of India. Dr. Nishit Gupta, MEITY, Government of India. Dr. Hemlata Gupta, MEITY, Government of India. Dr. Raj Singh, Siri Pilani. Dr. Nakhendra Krishnapura, IIT Madras. Dr. Nitin Chandra Chudan, IIT Madras. Other IIT Madras Cluster members. Director, IITDM Kanchipuram. Dean, SRICCE, IITDM Kanchipuram. SRICCE Cell, IITDM Kanchipuram. The HPRCSE team members work under SMDPC2SD project. Mr Dhayalakumar, Lab Engineer. M. Skanda Deepsita, Project Associate. Dr Noor Mahammad Sheikh, Chief Investigator. Thank you.